Okay, welcome back to this statics video in which we are analyzing the truss in problem 5.7. So far we have found missing geometry. We found the angle that these diagonal braces make with the horizontal truss members of 53.13 degrees. And we found the reaction forces, the vertical reaction at F and the vertical and horizontal reactions at E. We then analyzed joint F and found that member DF is in compression and carrying 153.3 kilonewtons of load, and that EF is a zero force member. It actually doesn't carry any load. So we're now going to move on to joint E. So we start by drawing a free body diagram of the joint, and we need to make sure we include all of the forces. We have the vertical reaction force. We have the horizontal reaction force. We would have a horizontal member from EF coming into the joint here, except we found that it is 0, so we can neglect that. Then we have the diagonal member that we will call DE. And we have a vertical member here that we can call CE. The angle that this diagonal member makes with the horizontal is 53.13 degrees. The vertical reaction force we found to be 46.7 kilonewtons. The horizontal reaction force was 30 kilonewtons. And if we were to take a guess at the sense of these forces, we know that this horizontal force here is pulling joint E to the left. Now, the horizontal member here is a zero force member, so it is not going to contribute to the equilibrium of this joint. Therefore, this 30 kilonewton horizontal load must be canceled out by a tension force in DE. It must be pulling away from the joint to the right. So DE is going to be in tension, we believe. And if we look in the vertical direction, we have the reaction force pushing up. We also have a tension force here in DE pulling up. So that's two forces going in the upward direction. Therefore, they must be canceled out by the force CE, which must be in compression. Or so we think. So our analysis will either prove or disprove this assumption, depending on whether our results give us a positive or negative answer. If we get a positive answer, our assumption was correct. If the answer is negative, we just need to flip the arrow on our diagram. Okay, so we can start in the vertical or horizontal direction here. I think horizontal is going to be the way to go in this particular case because the only unknown horizontal force is the horizontal component of DE. So the sum of forces in the x direction will equal 0, and those forces include the negative 30 kilonewton load, the reaction force at E in the negative direction to the left, plus DE times cosine, because we're talking horizontal, cosine of 53.13 degrees. So we solve for DE. DE is going to equal 30 divided by cosine of 53.13. So that is equal to, my calculator shows me 49.9998, but that will round, when we go to three significant figures, to 50.0 kilonewtons. And again, that's going to be in tension, so that's pulling away from joint E, 50.0 in tension, which means since it's pulling away from joint E, it's also pulling away from joint D, because tension is a pulling force. This one, again, is 0. And so now we can look at member CE in the vertical direction. which we can find by summing our forces in the y direction. That should equal 0. And those forces include a positive 46.7 kilonewton force, the reaction force at E in the vertical direction. We also have pulling up the vertical component of DE. So that's going to be 50 times sine of 53.13. The vertical, that's the vertical component. And that will all be resisted by CE, which is acting in the downward direction. It's a purely vertical member. So CE is going to equal 46.7 plus 50 sine of 53.13. So if we calculate that, I'm getting 86.7 kilonewtons. So that's 86.7 kilonewtons. And this one is in compression. So it's pushing down against joint E and also pushing up against joint C. So we've already found this truss member, DF, EF, DE, CE. So we found all 4 of these. So next we can move on to either joint C or joint D. Joint D is going to have fewer unknowns, so I think that's where we want to go next. So I'm going to write in on this diagram some of our known quantities. I'm going to do that with the recording paused. Okay, so I copied over some of the values that we've already calculated, including the compression force in DF. That was 153.3 kilonewtons. Pushing, it's compression, so it's pushing up against joint D. We had the force in DE was exactly 50.0. And that is acting at a angle of 53.13 degrees. Then we have this member CD framing in horizontally, and we have framing in from above in the vertical direction BD. So first we should take a guess at the sense of these forces. I'm going to guess that this large 153.3 kilonewton force is going to be greater than the vertical component of 50, and that's a pretty safe guess. So the net result of these two forces is going to be an upward push, which means that it has to be reacted by a downward push from BD. So it's going to be in compression. And since this 50 kilonewton force is pulling the joint to the left with a tension force, then CD must cancel it out by pushing to the right. So we can take a guess that CD is in compression. And then we can begin to solve for our unknowns. In this case, it doesn't really matter. There's no clear benefit to doing X or Y first. So I'll just say let's do X because it comes first alphabetically. So the forces in the X direction include CD, that unknown compression force in the horizontal member, minus the horizontal component of our force in ED. So that's going to be 50 times cosine of 53.13 degrees. So we solve for CD, and it is equal to 50 cosine of 53.13 degrees. And that equals 30.0 kilonewtons. So we've got 30.0 kilonewtons, and that's a compression force that pushes out both to the left and to the right. Next, we can sum the forces in the y direction. That will equal 0. And the forces in the y direction include our positive 153.3 kilonewton force, which is coming from member DF. We have the vertical component of 50 sine of 53.13 degrees pulling down in tension, and then we have pushing down member BD. So we solve for BD, and BD is equal to, that's going to be equal to 50 sine of 53 point, actually no, let's do this a little differently. In this equation, BD is currently a negative term, so to solve for it, all I really need to do is add it to both sides of the equation. So if I add BD over here, it becomes positive BD, and then this will be positive 153.3 minus 50 sine of 53.13. So the algebra can be a bit tedious, but you have to make sure you don't make any careless mistakes. Hang in there. That gives me 113.3 kilonewtons. And that's in member BD, and we said that was in compression. So it's pushing out in both directions. 113.3. So we're kind of working our way up the truss. We've found 1, 2, 3, 4, 5, 6 of the tension or truss forces so far. That leaves just 3 more to go. I'm going to recommend that we jump up here to the upper left corner. Let's take a look at joint A, because it's a bit unique in that it's very easy to find the forces at joint A. If we draw a free body diagram at joint A, we have an externally applied force of 100 kilonewtons in the vertical direction. We have an externally applied force of 10 kilonewtons in the horizontal direction. And then we have a vertical and horizontal truss member of 10 kilonewtons. Nope. We'll just call this AC and AB. Now there are no diagonal members framing in here. There are no diagonal externally applied forces. So all we have here are purely horizontal and purely vertical forces. So when this 10 kilonewton force gets applied to the joint, the only force capable of resisting it is AB. So it must be equal to 10 kilonewtons. And the vertical force of 100 can only be resisted by AC, so it must also be 100. And so just like that, without any calculation whatsoever, we know that this force is 10 and it's in compression, it's pushing against the joint, and AC is 100 and it is also in compression, pushing against the joint. So these types of joints that don't have any diagonal members or forces acting on them are really easy to solve for. So that brings our total now to 1, 2, 3, 4, 5, 6, 7, 8. We really only have this diagonal member now to solve for. Unfortunately, I'm running up against my 15-minute limit, so we're going to have to finish this truss analysis in the next video.